Suppose you take a screening test for a medical condition that occurs in 1 in 10,000 people, and, unfortunately, the screening test finds you to have the condition. You ask the doctor how accurate the screening test is, and, unfortunately again, the doctor says that it's 99% accurate. Things seem pretty dire for you, but actually, things aren't as bad as they seem. Let's reason through the probabilities at play here. We're concerned with the probability that you have the condition, given that you've tested positive to the screening test. So there are actually two probabilistic events: having the condition and testing positive on the test. Let's draw a tree diagram for these. The probability that any given person has the condition, according to its frequency, is 1 in 10,000, which means that there's a 9,999 out of 10,000 probability that any given person doesn't have the condition. Now from these events, we look at what happens with the screening test. The screening test is 99% accurate. So for the people who do have the condition, 99 for every 100 of them will be correctly told that they have tested positive, while 1 out of 100 of them will be told that the screening test came up negative, even though they do have the condition. For those 9,999 out of 10,000 people that don't have the condition, 99% of them will be told that they don't have the condition correctly, but 1% of them will be told that they do have the condition, even though that's not true. So multiplying these probabilities through, we can work out what proportion of those that tested positive to the screening test actually have the condition. And we can see that because there are so many false positives, the likelihood of you actually having the condition, given only that you've tested positive, is less than 1%. This might seem counterintuitive, but remember that there is only a 1 in 10,000 chance of having the condition. So this updated probability actually represents a 100-fold increase.